So we want to look at not just hypothesis tests for the average of something, finding out the average height in a country, or finding out the average opinion on something, or performance. We want to move on to proportions. Okay, we want to know between 0% and 100, or proportionally 0 to 1, how to test if certain percentages of populations exhibit some kind of behavior. Okay, so we're experienced with hypothesis testing so far, and so we can move through this fairly fast by just pointing out the small nuances between these. And for context, this is our new problem. Let's say we want to run new data-oriented management at our awesome pizza restaurant. Now, let's say I have a friend who told me about some of the really interesting pizzas she saw when she taught in Korea. So I thought it'd be really interesting to say, hey, we brought this shrimp and corn pizza, and we want to see if more than 60% of customers prefer this specialty pizza. So let's first always set up our hypotheses that we're testing. Step 1, state our hypotheses. We're testing hypotheses, we should know what they are. Our null hypothesis, remember that being the default that we're assuming, and we're trying to see good enough evidence to convince ourselves out of believing. This is the standard, this is the default, this is what we believe before we do the experiment, and then we have to be convinced out of what we believe. Okay, we assume that nothing interesting is going on until we see spectacular enough results to convince us that there's something going on. Let's say, on average, just for our pizza, that 60% of people tend to enjoy our general pizza. Like 60% of people enjoy pepperoni, 60% of people enjoy Hawaiian pizza. We'll just say the going rate of normal proportion for pizza is P is equal to 0.60 as a proportion, or 60%. Now we have our alternative hypothesis, the one that we're looking for so much evidence for that we convince ourselves into it if we have extraordinary enough evidence. Now we want to see, we're testing that more than 60% of customers prefer a new specialty pizza. So this is going to be a one-tailed hypothesis test, where we're looking at the upper edge of our statistical distribution. So we're going to say that we're testing if P is greater than 0.60. If people enjoy this pizza way more than average. Because I have confidence in our shrimp and corn pizza. Why not? We know all the steps, so we can probably collapse them into just our second step. Analyze the data, assuming that we collected it. Yeah, let's say we went out to handed 100 people, so our sample size is 100, handed 100 people a slice of this new pizza, and we asked if they enjoyed it. And let's say that 68 of those people enjoyed it. Okay, so our sample proportion, P hat, this hat meaning that we're estimating the population proportion, P hat, our quick estimate is that 68 out of 100 people enjoyed it, which means our proportion is 0.68, or 68% of the population. Now, this is when we have to reaffirm why we're doing hypothesis testing, because in this test, I mean, it looks like 68% of people enjoyed it, and we're trying to prove that our proportion is greater than 60%. So some people might be satisfied with saying, hey, that's larger. But that's why we do hypothesis testing, is to get like a statistical answer for if this is good enough. Because maybe 100 people wasn't good enough. Maybe we needed 500 people. Maybe we needed 1,000 people. This is New York, and there's just a huge population we need to worry about. 100 could just be such a small and insignificant number. Maybe for 100 people, we needed way more extreme results to be confident. So this is when we have to reach the steps where we say, is this significant enough to convince us from our default to our alternative hypothesis? So in this analysis, we have two steps. One is we find the standard error of a proportion. And we know that this formula is SEP is equal to square root of P 1 minus P all over N. Okay, that's given to you in the notes. And we have our proportion right here. That's equal to 0.68, 1 minus 0.68 all over, we sampled N people, which was 100. And we use little squiggles because we're rounding. This is an approximation. That's 0.0490. Okay, that's our standard error. This is just a number that represents the variation on it. This is a little standard error. This is a lot of standard error. Just finding the amount of uncertainty, variability in this data, essentially. Okay, but you just have to think about it like a big number that just helps us calculate something bigger. If you want to take a mathematical statistics class, I highly recommend it because that's usually where we derive all these things. Okay, now our second step in these calculations is to find the z-score, which is z is equal to p minus p naught over the standard error of the proportion. Okay, so we can literally just plug and chug at this point. This is our proportion that we sampled, which is 0.68. P naught is the default that we were assuming, our null hypothesis essentially, and so that was 0.60. So again, this whole top part is just finding how much our sample deviated from our assumed proportion. And that's all over, we already calculated the standard error, so that's 0.0490. Okay, and there's obviously still rounding here. So we're going to say the z-score is approximately 1.63. Lovely. Okay, so being a one-tailed t-test, now we want to find our p-value. Which remember is, if we assume that the null hypothesis is true, how likely is it that we saw data this extreme? This z-score representing all the factors, the standard error, the deviation of how extreme our proportion was, how many people were sampled. This is just a measure of how extreme our measurement was. And we just have to ask if it's extreme enough to convince us that the null hypothesis is wrong. This p-value is the probability of, if the null hypothesis was true, how weird would it be to see this extreme or more extreme data. So on our standard curve, which, as you recall, is calibrated to be averaged at 0, standard deviation of 1. We have this value on our one-tailed t-test, z, of 1.63. And so we want to find what's the probability that we saw this extreme of a value or more extreme. Okay, this sounds like we can use our calculators, but I like to get practice more with our z-table. And we say, hey, we're looking for an upper test. This one approaches from the left, and this one also approaches, but it keeps going to the right. So we have two options here, and both should get roughly the same answer. Well, if done correctly, they should get the exact same answer. We're just worried about the top tail, starting at 1.63. So what we could do is we can look at this first curve and get it and find the area up from negative infinity to 1.63. And so we'd get some number, and then we'd have 1 minus whatever this value is, because the area under this entire curve is 1. And so if we found 1 minus this whole area, then we'd find the upper area. But that also sounds like it might be a little complicated. So here's this easier version. Recall that this whole curve, this standard normal curve, is symmetrical. So if we find up until, let's say, because this is mirrored, negative 1.63, we found this area, then that should be identical to the upper area, 1.63. So in fact, we can look up negative 1.63 and see the probability that we're covering. So let's see, this is the third column, and we want to look for 1.63. Okay, so we get down here, 1.63. Okay, that says 0.0516. 0.0516, which says that there's a 5.16% chance that we'd see this extreme of data or more extreme. Now we're still abiding by the confidence that we were looking at before. When we created the hypothesis, or rather the hypotheses, we should say that we want to be 90% confident. We want to be 95% confident. We want to be 99% confident. But we dropped the ball, and we should have said at the beginning. So our default is usually 95% unless otherwise stated in this class. So with 95% stated, this is larger than 0.05 for 95% confidence. So this would actually fail our hypothesis test. This means we do not see significant enough results to reject the null hypothesis. We fail to reject the null hypothesis. So we cannot conclude that our amazing new corn and shrimp specialty pizza from Korea is preferential to our customers. Which is sad, but we can always find fun and new pizzas somewhere else to try.